Welcome to lecture 35. This is our second lecture on quantum optics. And in this lecture, I'm going to try to give you some of a sense of how LIGO works and also how using squeezed states of light, one can improve the accuracy of LIGO. So to do that, we're going to talk about how we measure these quadratures QL hat and PL hat, which are analogous to position and momentum if you think about light as a harmonic oscillator, and we introduced them in the last lecture. We'll also discuss how we can reduce the uncertainty of either Q or L at the expense of a higher uncertainty for the other quadrature in the pair. And then we'll show how LIGO employs these ideas for even higher precision. I want to comment on the fact that if you went out and tried to directly measure the electric field of light, you would get zero. And that's because the light simply oscillates too fast. The fastest oscilloscope that I'm aware of runs at about 100 gigahertz. Most oscilloscopes that experimentalists would use would be operating more on the range of 10 gigahertz or so. And light's oscillation frequency is on the order of 10 to the 14 to 10 to the 15 hertz, which is 3 to 4 orders of magnitude faster. Nevertheless, there are some schemes that will allow us to actually measure the fields of light by employing what are some rather clever techniques. And the first one that we're going to discuss is something called heterodyne detection. This involves measuring the signal from two light beams whose frequency differs by a very small amount. It has to be less than 10 or so gigahertz. And then you observe the beats between those signals, which will oscillate much more slowly than the light beams themselves. So let's see exactly how this works. The way heterodyne detection is set up is very similar to the experiments we were talking about before with a beam splitter. Here I have the similar setup where I have input ports 1 and 2. We have the silvered side of the beam splitter on the bottom, and we have exit ports 3 and 4. We're going to be measuring in port 4, and we're going to be putting in two beams. So we're going to have a beam of light described by a semi-classical light with a parameter alpha 1 coming into port 1. And we're going to have a beam of light with a semi-classical parameter alpha 2 coming into beam 2. In the experiment, you should be thinking of the light that's going into port 1 as being a weak light signal. That's the signal we want to measure, and we're inputting a very strong signal into port 2. That's used to boost the signal that we're going to measure. And the detector is entirely in port 4. So the input state is this tensor product of alpha 1 with alpha 2. Remember, alpha 1 and alpha 2 are the coherent states of light for a particular mode of light with a parameter alpha in that mode. And the photocurrent is going to be given by the electric charge multiplied by the number of photons that I'm detecting. And that's going to be given by the area S, the cross-sectional area of the light beams, multiplied by this single photon probability amplitude squared, which is given by W of 1 of R4 and T. And we know the formulas for that. It's just QE times big S times little s, that's the sensitivity, multiplied by the modulus squared of E4 plus, evaluated at R4 and T, operating on the initial state psi in, and I take the modulus squared of that. Now, the strategy that we use to solve these problems is we always relate the output fields to the input fields. So E4 plus is just equal to the transmission amplitude T times E1 plus minus R times E2 plus, and that minus sign is coming in because port 2 is going through the glass side of the beam splitter. We're going to assume the frequencies omega 1 and omega 2 are close so that we can approximate this single photon amplitude epsilon 1 of omega 1 to be approximately the same as epsilon 1 of omega 2. And we're going to call that epsilon 1 of omega, where omega is the average frequency between the two light beams. The photocurrent then becomes QE times big S, the cross-sectional area, times the sensitivity, times the square of the single photon amplitude, multiplied by the modulus squared of T alpha 1 e to the minus I omega 1t minus R alpha 2 e to the minus I omega 2t. The alpha 1 and alpha 2 are coming out because the A operator for mode L acting on psi in will pull out alpha 1 when it corresponds to the 1 field, and it'll pull out alpha 2 when it corresponds to the 2 field. Now you can see that these have two different frequencies, and so when I take the modulus squared of that, I'm going to get some terms that don't depend on time. Those are the modulus squared of each of the terms. And then the cross terms are going to depend on time, and that's where we're going to be seeing the signal that we're going to be focusing on. So evaluating that norm then gives us absolute value of t squared, absolute value of alpha 1 squared, plus absolute value of r squared, absolute value of alpha 2 squared, minus 2 real part of r times t star times e to the I omega 1 minus omega 2 t times alpha 1 star alpha 2. We're going to let alpha 1 be represented by its modulus, absolute value of alpha 1 times its phase, e to the I phi 1. Alpha 2 will be the same, modulus alpha 2 e to the I phi 2. And we're going to assume r and t are both real. And then we get the following expression. I4 is QE big S little s, the single photon amplitude squared multiplied by modulus of t squared, alpha 1 squared, plus r squared, alpha 2 squared, minus 2 RT, modulus of alpha 1, modulus of alpha 2, cosine of omega 1 minus omega 2 times t, minus phi 1 plus phi 2. Those are the two phases corresponding to the semiclassical states. Now, you recall in the last lecture we showed that the sensitivity multiplied by the square of that single photon amplitude could be rewritten as this quantum efficiency eta divided by the area S times the time t over which the measurement is being taken, and that was for the case where we had light moving in a cylindrical quantization volume. And you have to recall as well that the modulus of alpha squared is proportional to the number of photons in the quantization volume, because the expectation value of the number operator in the semiclassical state is just the modulus of alpha squared. Of course, the number of photons in the volume is going to increase as the length, because L is equal to c times t. That means the number of photons is proportional to the time interval over which I'm performing the measurement. But the photon flux, which we call phi photon, is equal to alpha squared over t. That is something that is independent of time. You can think of it, if you like, as a density of photons. And it's very common to talk about the beam intensity as an energy density, which is given by phi without the phot subscript. And that is just the number of photons multiplied by h bar omega, the energy for each photon. And in terms of that, the beam intensity satisfies the energy density phi divided by h bar omega is equal to modulus of alpha squared divided by t. Or we can invert this to determine what the modulus of alpha is in terms of the beam intensity, and we get the modulus of alpha is equal to the square root of phi t over h bar omega. That's going to be an important relation that we're going to be using. So if we plug that into the signal, what we find is I4 of t is going to equal the quantum efficiency eta times the electric charge QE multiplied by t squared times phi 1 phot. That's the photon flux in terms of numbers, plus r squared phi 2 phot minus 2 RT, the square root of phi 1 phot phi 2 phot, times the cosine of omega 1 minus omega 2 times t minus phi 1 plus phi 2. And if we tune r and t in such a fashion that t squared times the intensity in channel 1 is equal to r squared times the intensity in channel 2, then we get I4 of t will equal 2t squared phi 1 phot eta QE times 1 minus cosine of omega 1 minus omega 2t minus phi 1 plus phi 2. That would give us a visibility that's exactly equal to 1. But the key point is actually in the equation above. You see, instead of having to measure phi 1 phot, which is very small because we have a weak signal that's coming in, the amplitude of the oscillation is given by the square root of phi 1 phot times phi 2 phot. So if I put in a very large signal in the port 2, that boosts the amplitude by a quite substantial amount over the very small amplitude I'm trying to measure. And it actually seems like we're getting something for nothing. So in order to really verify this, we should look at the signal to noise for the two different types of measurements to see if there is really a gain. And for that, we have to compare to what would happen if we just directly measured the weak signal. This would entail having no beam splitter, and then the measurement would simply be given by eta, the quantum efficiency of the detector, times QE, times that photon flux for the incoming beam, that weak beam, And we have to compare that to the photocurrent for this heterodyne detection, which is eta QE R times T times the square root of phi 1 phot, phi 2 phot. And what we have to consider is the noise, which is white noise. It's also called shot noise. I don't have the time to fully derive this expression here. It's not all that difficult to derive, and you've probably seen it somewhere before, especially in an experimental physics class. But the noise or the fluctuations in the direct current would be given by the square root of 2QE times that direct current times delta F, where delta F is equal to 1 over the time interval I used to make the measurement, which is called the bandwidth. So if I now look at the signal to noise ratio for the direct measurement, I get I direct over that square root of delta I direct. And when I cancel out the terms, that becomes the square root of I direct divided by 2QE delta F. And that's the square root of eta phi 1 phot divided by 2 delta F. If I look at the same thing for the heterodyne detection, here the noise I have to put in is the noise corresponding to the very large signal, because that's going to overwhelm the noise from the small amplitude. So I'm going to have a square root of 2 QE squared eta phi 2 phot delta F multiplied by an R, because it's only the light that is reflected that is going to dominate the noise, but because that phi 2 signal is so much bigger than the phi 1 signal, and the noise adds in quadratures, it's essentially entirely phi 2 phot noise. And when I evaluate that, we get T multiplied by the square root of eta phi 1 phot over 2 delta F. And you see those are essentially the same. The only difference is this factor of T. So that seems like there's absolutely no gain to doing the heterodyne detection. But you have to be careful. This analysis ignored what's called dark current noise. So within every detector, even if I make it very cold, I will get some counts that come in simply from ambient noise of photons that are around, or simply because the detector itself has some thermal excitation of electrons. And that noise is something that can drown out a very weak signal. What you can do with heterodyne detection is you can actually measure a photocurrent that is substantially less than the dark noise by using heterodyning, because you boost the amplitude of the signal above the dark noise signal from the square root of phi 2 phot, and the signal to noise ratio is still the same as if I was measuring the weak signal directly, but that signal to noise ratio can be made large enough that I can actually do the measurement. And so with heterodyning, you can actually measure photocurrents that are significantly smaller than the dark current if this alpha 2 is large, and that's the real benefit of this approach. Okay, we're now going to talk about something called balanced homodyne detection. This is a twist on the heterodyne detection where we're going to send in the exact same light in both of the channels. So the two frequencies are going to be the same, the two wave vectors are going to be the same, the two polarizations are going to be the same. So there's actually no oscillation term now. There's going to be just an overall constant phase factor that's going to be multiplying that state that I have to take the norm of, and I can take that constant phase out and it will leave me just a constant photocurrent. And what we're going to be measuring now is the difference in the photocurrents, I3 minus I4, between those two channels. Let me go back to the beam splitter again to show you what that means. What we're going to be measuring now is not just the detection of the I4 current. We're going to put another detector at I3, and we're going to measure the difference of I4 or I3 minus I4. In order to do that, the measurement, we have to look at what is the measurement results for the different channels, and over a time interval t, that's going to be the cross-sectional area S times the time interval t times this probability amplitude squared of the single photon detection, W1 of 3,4 evaluated at R and T, and that's equal to eta times the absolute value squared of psi multiplied by n, 3 or 4. And that tells me I3 of 4 is just eta QE divided by T multiplied by the modulus squared of this n operator. So what we need to do, since we're measuring the difference of these two currents, is we need to express N3 minus N4 in terms of those input creation annihilation operators. And in balanced homodyne detection, we always take r equals t equals 1 over the square root of 2. And so that allows us to evaluate these number operators. I'm going to move the page up so that we can focus on evaluating n3 minus n4. What we find is n3 is equal to r a1 dagger plus t a2 dagger multiplied by r a1 plus t a2. You notice here that the number operator exactly transforms as the E3 plus operator would transform. And we get a similar result for n4. When we multiply that out, we're going to get 1/2 a1 dagger a1 plus a2 dagger a2 plus a1 dagger a2 plus a2 dagger a1 for the n3. And for the n4, because of the minus sign that's coming in under reflection coming from the glass, we get a 1/2 a1 dagger a1 plus a2 dagger a2 minus a1 dagger a2 minus a2 dagger a1. So when we take the difference, n3 minus n4, we get twice this cross term, and it's equal to a1 dagger a2 plus a2 dagger a1. Again, what we're going to do is we're going to represent this semi-classical parameter alpha. We're going to call alpha 2, which is the very big signal. That's going to be called the local oscillator signal alpha LO, and that's going to be given by the modulus of alpha LO times e to the I phi LO. And then I3 minus I4 is equal to eta QE over T, the matrix element psi 1, A1 dagger psi 1. I'll have an alpha LO modulus and e to the I phi LO. That term is coming out from evaluating the expectation value of A1 in the state phi 2, which is given by the semi-classical state with parameter alpha LO. So that evaluation just gives alpha LO. And in the way we're writing it, we write it as the modulus times the phase. And then it's going to be plus psi 1, A1 dagger psi 1, modulus of alpha LO times e to the minus I phi LO, because that's the expectation value of A2 dagger. Now I'm going to put all of that together into the same expectation value. And the matrix element is now psi 1, A1 dagger e to the I phi LO plus A1 e to the minus I phi LO psi 1. And I can now re-express that in terms of the real and imaginary parts. I'm going to get a psi 1 times A1 dagger plus A1 psi 1 cosine phi LO plus I psi 1 A1 dagger minus A1 expectation with psi 1 sine phi L0. And what you see is coming in here are the quadrature amplitudes. A1 dagger plus A1 is proportional to Q1 hat, and I A1 dagger minus A1 is proportional to P1 hat. So what this is telling you is that the measurement of the photocurrent, I3 minus I4, in a balanced homodyne detection is a direct way of measuring either one of these quadrature amplitudes, either Q1 or P1, and I can adjust which one I'm measuring by adjusting the phase of the local oscillator. By changing that phase, if phi LO is equal to 0, I'm going to measure the Q. If phi LO is equal to pi over 2, I'm going to measure the P. So using this balanced homodyne detection, we can measure the quadrature operators as functions of the local oscillator phase. You should note as well that this result is independent of the time interval t because the number of photons grows linearly in this time interval. And that's because the overall signal was divided by this factor of 1 over t. All right? So now we need to also discuss the fluctuations in noise because we need to know what our signal to noise ratio is. So we're going to look at n3 minus n4 quantity squared. That is easy to calculate. It's this A1 dagger A2 plus A2 dagger A1 quantity squared. And you get 4 terms, A1 dagger A1 dagger A2 A2 plus A1 dagger A2 A2 dagger A1 plus A2 dagger A1 A1 dagger A2 plus A2 dagger A2 dagger A1 A1. We want to put these into normal ordered form, which means put all of the dagger operators to the left using the commutation relation, and we find we get A1 dagger A2 A2. That was already normal ordered. We don't do anything with that. Plus A2 dagger A2 A1 A1 plus A1 dagger A2 A1 A2 plus a correction term, which is A1 dagger A1 plus A2 dagger A1 dagger A1 A2 plus a correction factor, which is A2 dagger A2 plus A2 dagger A2 A1 A1. That last term actually shouldn't be there because I already wrote it in the first line. So that last term should not be there. I'm going to blur that out so you don't get confused by that. Now, when we take the average with respect to alpha LO, remember the A2 operator is going to go to alpha LO, the A2 dagger is going to go to alpha LO star, and I'm actually going to, for simplicity so that I keep all my terms, I'm going to not worry about the normal ordering of the A1 dagger term because that's multiplied by the alpha LO squared. You'll see why I do that in just a second. That's so we can write that matrix element as the square of something. But you see that all of the terms except for one are multiplied by this alpha LO modulus squared. And remember, alpha LO is a very big signal that I'm putting in. And so alpha LO squared is huge. On the other hand, the term psi1, A1 dagger, A1, psi1, that's very small because that is the weak signal that I'm trying to measure. So we're going to neglect that because it's small. And you see what we're going to get then is I can rewrite this as alpha LO squared times the operator squared, A1 dagger e to the I phi LO plus A1 e to the minus I phi LO quantity squared minus the operator psi1 A1 dagger e to the phi LO plus A1 e to the minus I phi LO expectation value quantity squared. And that's just the fluctuations of this operator, A1 dagger e to the I phi LO plus A1 e to the minus I phi LO, the whole thing multiplied by alpha LO squared. And I'm evaluating that fluctuation in the state psi1. Now, that operator is very similar to the Q operator. We're going to define a new operator called Q1 of phi LO, which is exactly that operator. And then recalling that Q1 is equal to the square root of h bar over 2, A1 plus A1 dagger, and P1 is minus I, the square root of h bar over 2, A1 minus A1 dagger. That tells us that when phi LO is equal to 0, we're going to get Q. And when phi LO is equal to pi over 2, we're going to get P. And this operator as a function of phi LO actually will interpolate between these two. Before moving further, I want to remind you of what the expression is for the electric field amplitude. E of R and T is the sum over all modes L, the polarization epsilon L, the single photon amplitude epsilon 1 of L, square root of 2 over h bar, multiplied by minus QL operator sine KL dot R minus omega LT, minus PL operator multiplied by the cosine of KL dot R minus omega LT. It's a little unfortunate that the minus sign is there, but that's simply the way that it is. And so what I can do is I can interpret Q as the real part of the amplitude of E, and I can interpret P as the imaginary part of the amplitude of the electric field. That's in terms of each of the pieces of the two complex conjugates that we're adding together, because of course we set up the electric field to always be real, so you can think of imaginary part and real part perhaps in quotes, but we kind of know what we mean by that. In other words, there are these two complementary amplitudes of the electric field, and they're given by these quadrature variables. So by measuring the quadrature variables, I'm actually measuring essentially the amplitude of the electric field. Now, in general, when I consider a Q of theta and a Q of theta plus pi over 2, I can think of those as a Q of theta and a P of theta, and they actually satisfy the canonical commutation relation. Q of theta commutator with P of theta is equal to IH bar for all theta. We worked it out directly when theta is equal to 0. I leave it as an exercise for you to work that out as a function of arbitrary theta, but it's fairly easy to see that's going to hold. Now, what we're going to do is we're going to be using those quadrature operators to measure the field. We're going to, again, consider that our state coming in is a psi1, which is a semi-classical state alpha 1 that is weak. It's given by absolute value of alpha 1 times e to the I phi 1. And then this measurement of Q of theta, we just plug in what the operator is, and we can just immediately evaluate it because the A1 dagger goes to alpha 1 e to the I phi 1, e to the minus I phi 1, and the A1 goes to alpha 1 e to the I phi 1. So you see that the expectation value of Q of theta is just square root of 2h bar cosine theta minus phi 1. And similarly, if you evaluate P of theta, we'll get minus square root of 2h bar sine of theta minus phi 1. We want to look at the variances as well. You have to be careful when you evaluate the variances because one of the terms, A1 dagger, is not in the correct order. We have to use the commutation relation to change the order of that in order to be able to evaluate the A operators acting to the right on the alpha state and the A dagger operators acting to the left on the alpha 1 bra. And when you do that, you'll get h bar modulus of alpha 1 squared times cosine 2 theta 1, theta minus phi 1 plus 1 plus h bar over 2. I can use a trig identity, the double angle formula, to rewrite that as 2h bar alpha 1 squared cosine squared theta minus phi 1 plus h bar over 2. And if you go through the same exercise with p of theta squared, you find there's just a couple of sign changes. It changes to cosine 2 theta minus phi 1 minus 1 plus h bar over 2. And that actually is equal to 2h bar alpha 1 squared sine squared theta minus phi 1 plus h bar over 2. And so what we find when we subtract the expectation value squared, those trig functions disappear. So subtracting q of theta squared, that's equal to 2h bar cosine squared theta minus phi 1. I forgot there's an alpha 1 modulus that is missing in that expectation value of q of theta and of p of theta. I apologize for that. Both of those should have a modulus of alpha 1 in them. So that's those two trig functions are going to cancel in the fluctuations, and we're left with the h bar over 2's for both the delta q of theta and the delta p of theta, and when I multiply them together, I'll get h bar over 2, and that tells me that these semi-classical states that I'm working with are minimal uncertainty states. We've known that for a long time about the simple harmonic oscillators because they're simply shifting the ground state to a different origin. And we're going to now take this result and we're going to plot it in a quote-unquote phase space where I'm going to be using as the variables on the axis, the horizontal axis will be q, the expectation value of q divided by square root of 2h bar, and the vertical axis will be the expectation value of p divided by square root of 2h bar. And that tells me my uncertainty relation is given by a circle in this phase diagram that has a diameter equal to 1. The vacuum state corresponds to this sitting at the center where alpha is equal to 0. And any of these semi-classical states simply displace that circle in this phase space by the value alpha. And the time dependence is given by alpha goes to alpha e to the minus I omega t. That's something we worked out earlier. And so that's going to involve a clockwise rotation of that circle along a radius that has a radius given by alpha. Now the uncertainty, because it's a circle, no matter how it rotates, as the alpha vector moves, traces out a circle in this plane with a frequency given by omega, the uncertainty of a measurement in either the p direction or the q direction is always equal to 1. The uncertainty never changes as a function of time. Now when we look at squeezed light, which is the next thing we're going to look at, it's going to trade off the uncertainty for q into an uncertainty for p, and we're going to see that this result no longer holds. I'm going to ask you at this stage to actually pause the video and go back and review what we talked about with squeeze states. It's important to do that so you understand how we work with squeeze states. It will help you understand the analysis that we're going to be doing that's going to show how squeeze states can improve the measurement of these quadrature operators. So I'm going to ask you right now to pause the video as we look at the squeeze and go and look at the lecture on squeeze states. Okay, thank you for doing that review of squeeze states. I want you to recall from that problem on the homework which was called the Bogoliubov transformation, we defined these capital A operators, hyperbolic cosine of r times a hat plus hyperbolic sine of r times a hat dagger, and the dagger of those representations, and we could see that the commutation relation of capital AR with capital AR dagger was equal to hyperbolic cosine squared of r minus hyperbolic sine squared of r. You may or might not remember that the hyperbolic trig identity, but that is equal to 1. And we're going to consider these as squeezed operators, and they're going to be acting on squeezed states. The squeezed states are going to be just like coherent states. They're going to be eigenstates of this capital AR operator. So when AR acts on this operator, the squeeze state alpha comma R, that's going to equal alpha times alpha comma R. This is generalizing the coherent state, which is what we would get if R is equal to 0. Now, it's very important that we understand the inversion between these capital AR operators and the little a and little a dagger operators. That inverse is very easy to work out. I've written it down for you here. A hat is equal to cosh R, A hat big A R minus sinh R, big AR dagger, and A dagger is just the Hermitian conjugate of that. Now, we want to calculate the expectation value of the field in one of these squeezed states. We're going to get the I times the polarization times the single photon amplitude, and we're going to express that in terms of the A and A dagger operators, which we can express in terms of the big A dagger operators. And when a big A acts to the right, it gives an alpha, and when a big A acts to the left, it gives an alpha star. So it's very easy to evaluate this expectation value. We're going to just get cosh R alpha minus sinh R alpha star, e to the I k dot R minus omega t plus its complex conjugate. Now this is the same average as we would get for a quasi-classical state if I used alpha quasi-classical equals alpha cosh R minus alpha star sinh R. And if I look at re-expressing that in terms of the real and imaginary parts, that's actually a very useful thing to do. You get real part of alpha times e to the minus R plus I times the imaginary part of alpha times e to the R. Now, if alpha is real, then alpha quasi-classical is just equal to alpha times e to the minus R. And that's a very useful relation that we're going to be using. All right, as with everything that we do, we have to work more on just calculating the average values. We need the variances as well. And so we're going to calculate the variance of this measurement. It's exactly the same as before, but we're going to have to use the AR. We have to convert the little a's into the big A's, and we're going to find that the only contribution is going to come from the commutator of a big A with a big A dagger when we look at the expectation value of the square of the electric field minus the expectation value of the electric field quantity squared. We've gone through these kinds of calculations many, many times. I'm going to just tell you what the answer is. I encourage you to go through and work it out. It really just takes a few lines to calculate, and you really should do it to make sure you understand how this stuff works. What it's going to give you is the single photon amplitude squared multiplied by e to the 2r cosine squared minus omega t plus e to the minus 2r sine squared minus omega t. Now, this is very different from what we got in a quasi-classical state. In a quasi-classical state, we just got a number, and it was independent of time. But here you can see the fluctuations in the field are changing as a function of time. And what we're going to do is we can now plot this in this phase space plane where I'm plotting q over square root of 2h bar in the horizontal axis and p over square root of 2h bar on the vertical axis. What you find is the uncertainty gets squashed into an ellipse, and depending upon whether r is bigger than 0 or r is less than 0, the orientation of that ellipse changes. But now, as you remember that this state alpha r, it's going to also rotate with this omega t, you can see the uncertainty in q and the uncertainty in p are going to change as a function of time. So r greater than 0 has the best accuracy when the field amplitude is large. That corresponds to a measurement of the q quadrature. And r less than 0 has the best accuracy when the field amplitude is 0. And that's actually the way that you measure the phase, because the phase is determined by exactly where the electric field intersects the horizontal axis, so where the field goes to 0. So if I want to measure the phase, I'm going to want to do the quadrature that's going to be focused on measuring when the field is equal to 0. All right, so let's go look at what happens when we measure this on a beam splitter. What we're going to think about is we have this squeeze state of light coming in, and we're using a beam splitter to model loss in the signal. So we have this beam alpha r coming in. It can get reflected into the 3-channel, or it can be transmitted straight through. We're going to be working with a beam splitter where the reflection is very small, and we're going to think of that reflection as being a loss of this squeezed state due to reflection off of the optics in the system or other things. Absorption in the air could also be something that would lead to loss. We're just using this beam splitter to model the situation of if I had squeezed state and I lost some of my signal from the squeezed state, what happens? That's the question we're trying to answer with this. So we're putting no light into the second channel. We're putting the squeezed light into the first channel. We want to measure the light that is transmitted. We're going to use the measurement of the Q quadrature in order to do this. So the loss is given by the small value of R, or a t that is less than 1, because of course, as you remember, r squared plus t squared is equal to 1. Okay. Enough about the explanation. Let's go to the calculation. The Q4 quadrature operator is just the square root of h bar over 2, A4 plus A4 dagger. I have to convert that into the little a's of the input state. So that's TA1 minus RA2 plus TA1 dagger minus RA2 dagger. I have to convert the A1 and A1 dagger into the big A operators. We've seen that's an easy thing to do. I just substitute that in, and now I get a final result that is square root of h bar over 2 t ar e to the minus r plus t a dagger e to the minus r minus little r a2 minus little r a2 dagger. And now I'm ready to do the measurement of the average value of Q4. I get square root 2 over h bar t e to the minus r times 2 alpha for alpha real. That corresponds to a diminution of the Q4 quadrature by this factor t, which is less than 1. When I look at the fluctuations, I'm going to get two contributions. There's a contribution to the fluctuations that's going to be h bar over 2 t squared e to the minus 2r. That is coming from the calculation of the fluctuations of the squeezed state. But I also get a plus r squared, which is coming from the vacuum fluctuations of the light, which is just a vacuum that is input into channel 2. The vacuum fluctuation, if they're big enough, will overwhelm the t squared e to the minus 2r, which is the reduction in the fluctuations that I was getting from the squeezed state. So the result of this simple calculation tells us that if we lose signal from our squeezed state, it will remove all of the benefits of the squeezing in trying to reduce the fluctuations or the errors in the measurement. So when we work with squeezed light, we have to work with mirrors and optics that are incredibly good. Now, it was 40 years ago when Carlton Caves showed in 1980 how squeezing can help one do a measurement on a Mach-Zehnder interferometer. Now, we haven't really gone through a full description of a Mach-Zehnder interferometer, and I don't have the time to go through the full analysis using all of the formalism of quantum optics, but I want you to focus. If you focus on the upper part of the Mach-Zehnder interferometer, you see that's a beam splitter. That's the same analysis as we've been looking at before. And if you look at the lower part, that's also a beam splitter. So essentially, working with the results that we've done with the beam splitter, we can actually do the analysis of a Mach-Zehnder interferometer. It really just involves two steps of the beam splitter plus the reflection off the mirrors. And it's relatively simple to do. I just don't have the time to go through it here. What we're going to be doing, however, is a balanced homodyne detection at the lower right, under the assumption that I am sending in light that has the same frequency on both channels. So what we're going to be thinking about doing is we have the semi-classical light, an alpha that's much bigger than 1 that's going to channel 2, and we have either a vacuum or a squeezed vacuum that's going into channel 1, and we're trying to measure this semi-classical light. And again, we're doing balanced homodyne detection. We're measuring the difference in the photocurrent on the two ends. And we know how that measurement works. It's going to be proportional. The average value will be proportional to the expectation value of n5 minus n6. That's given by alpha, the square root of 2 over h bar, the expectation value in psi1 for the quadrature operator p1. And the fluctuations are given by the square of those operators, and that's given by alpha squared 2 over h bar times the expectation value in state psi1 of p1 squared. So the fluctuations are determined by the fluctuations of the quadrature operator P1 in the input state psi1. If I use an ordinary vacuum, those fluctuations are just h bar over 2 because this is a minimum uncertainty state. But if we use a p-squeezed vacuum, the uncertainty is h bar over 2 e to the 2r. And if we let r be less than 0, we're going to get an improvement on the measurement. Now I want you to note the name squeezed vacuum is in some sense a little bit of a misnomer. The squeezed vacuum has photons in it. It has photons in it in a particular arrangement that allows us to reduce the uncertainty in this quadrature variable. It is very fragile, as we saw, because the gains of this squeezing are reduced with losses in the light from the squeezed vacuum. So you need super high quality mirrors and optics in order to do experiments with squeezed light. The gains are huge in LIGO, however. An improvement in an accuracy by 1 plus delta will increase the volume of the observed universe by 1 plus delta cubed. So even a small improvement will create a huge increase in the observable universe that we can observe gravitational wave phenomenon. Okay, we're getting close to the end. We're now at the stage where I can talk about how LIGO works. LIGO is an interferometer. Gravity waves are quadrupole waves, which means I can't measure it with a single arm interferometer. These interferometers look like Michelson-Morley interferometers, not the Mach-Zehnder interferometers, but the basic principles are very similar. What I have to look at is a compression along one of the arms and an expansion along the other arm occurring at the same time. That's kind of like what we would call a D-wave excitation or a quadrupole excitation. In LIGO itself, each arm is 4 kilometers long, and it can detect differences in the lengths, delta L over L, that are equal to an astonishing 10 to the minus 21. To put this in perspective, using the fact that those arms are 4 kilometers long, that means it's an absolute measurement of 10 to the minus 18 meters. That is 1/1000th the radius of the nucleus. The radius of the nucleus is 1/100,000th the size of an atom. And this is 1/1000th the radius of the nucleus. That's how accurate LIGO is, and that's how accurate it needs to be in order to measure these gravity waves. So in order to try and do that, they use resonant cavities, which increase the effective length of those LIGO arms by a factor of 300. So they actually look like 1,200 kilometer long arms, even though they're only 4 kilometers long. The interferometry can measure distances that differ on the order of about 10 nanometers. That's with optical light that has a wavelength on the order of about 500 nanometers. So the length difference that I get just from the interferometry is 10 times 10 to the minus 9 meters, that's 10 nanometers, divided by 300 times 4,000 meters, that's the effective length of the arms. That gives me 10 to the minus 14. I believe the other 7 orders of magnitude are coming from the alpha squared from the lasers, but I have not been able to confirm this. But clearly they work with these very high power lasers, and the alpha squared has to be coming in to the sensitivity, and I believe that that's where the extra 7 orders of magnitude are coming in to give this ultra high precision of 10 to the minus 21. All right, let's take a look at what this means. So here is, again, a figure that I've taken from Alan Aspect's course on Coursera. The squeezed vacuum reduces the noise by 28%, and 1.28 cubed is about 2. So that tells me that twice as much of the universe can be absorbed when I put in a squeezed vacuum on the arms of those interferometers. I'm going to now do a close-up of this figure from the course. The red curve is the noise that is being measured in LIGO as a function of the frequency of the signal that is being measured. The axes are a little bit hard to see, but they're running from about 100 to 1,000 or so hertz. Those are what the two labels are. And the sensitivity, the axes there are 10 to the minus 22 is the upper one, and 10 to the minus 23 is the lower one. This is a log-log plot, and you can see it's actually getting sensitivities that are closer to a few times 10 to the minus 22. The red curve is original LIGO measurements. The blue curve is the enhancement due to using a squeezed vacuum as the input into the interferometer. And you can see it doesn't look like it's that much, but it is a 28% improvement. And again, that means that LIGO will be able to sample events over twice as large a volume in the universe. So that little difference is actually a huge effect in the sensitivity to gravitational waves that LIGO will have. And this has been a ad hoc mock-up that they put into the original LIGO. The new design of the improved LIGO is going to have the squeezed light designed into the LIGO from the start, and it's likely to achieve even higher accuracy than what has already been achieved, which is completely astonishing. And this really is part of a second quantum revolution, because you could not do this experiment and this improvement in the sensitivity without using the quantum optics and the phenomenon of squeezed light to reduce the fluctuations, which is what gives rise to the noise, which in the end determines overall what the sensitivity is of the instrument to measuring the particular gravitational waves that it's trying to measure. I wish I could explain to you exactly why the curve has this dip in the center and has the rising results on the two ends. I believe the high frequency end is coming from white noise. I'm not completely sure why the rise is occurring in the low frequency end. Nevertheless, I'm simply not an experimentalist, so I don't understand enough about these different noise features to be able to explain everything to you. But I hope you have a much better sense now about exactly how LIGO works and how quantum mechanics and quantum optics is used to improve it. That's it for lecture 35. We'll see you again in lecture 36.